So this is the first example in the section on optimization. So optimization problems are often like this, so they look like word problems, and I included some steps in the notes about how to solve these, right? So in general, these are good steps to try to follow. Okay, so if we read our first example here, and notice the first step is really read the problem. Okay, so if we read our first example, we want to make a cylindrical can that holds 2 liters of oil, and we want to find the dimensions that will minimize the cost of the metal needed to manufacture the can. Okay, so we want to make a can that holds 2 liters of oil, but we don't want to spend too much on the metal needed to make the can, right? So we want to find the dimensions of the can that will use the least amount of metal possible, right? So that will minimize the amount of metal that we need, okay? But the can does still need to hold 2 liters of oil, okay? So that's what this is saying, right? So we've done step 1, right? We read the problem and read the problem again, right? So we want to make a can holds 2 liters of oil. We want the dimensions of the can that will make it so that we spend the least amount possible on the metal needed to manufacture the can, okay? So we also want to draw a picture, right? So we want to draw some pictures and then try to label the pictures as much as we can so that we have some variables to work with. Okay, so if you look down here, that's what I did down here. So I drew us a can. So you can see here we need a top for the can, a bottom for the can, and then we need a body for the can, right? So this body, you can kind of form it from one sheet of metal like this. So if you take a sheet of metal like this, something flat, a rectangular kind of shape like that, you roll it up right a little bit, goes like this, and then you finally seal it, maybe put a weld or something like that down the side here, then you have this circular cylindrical shape, okay? So this is going to be useful for when we try to write down an equation for the next few steps, right? So notice here I labeled the things that are relevant. So because in the problem we're being asked to find dimensions of the can, I wrote down what the radius for the can should be, right? What the radius for the circle should be. So that's this R. And what the height of the can should be, right? How tall should the can be? Okay, so that's what this H is, okay? So we've done essentially step number 2, right? We drew a picture, we labeled the relevant quantities, okay? So step 3 is the optimization step, right? So here we want to write down an equation using the variables that we just declared here. So an equation for the thing that we want to optimize. Okay, so in this case, what we want to optimize is the equation that gives us the surface area for the amount of metal that we need. Okay, so we want to minimize something, that's the optimized part. And what we want to minimize is the amount of metal that we need to make this can. Okay, so all of these different components for the can are going to come from a sheet of metal, and we want to use the least amount of metal possible, right? So the amount of metal that it takes to create this top plus this bottom plus this body of the can, we want to use the least amount possible, okay? So that gives us an equation that we want to optimize, right? So maybe I'll write down step 3 here. So this was all really step 2. Step 3, so we want to let S equal the surface area of the can. Okay, so this is really telling me how much metal I need, right? So if I try to write down an equation for it, right, S equals, okay, so if we think about this, we need enough metal to create this top and this bottom. Okay, so notice those two are circles, right? So we're going to need essentially enough metal to cover the area of those circles. Okay, so the area of a circle, if you remember, it's pi r squared, okay, where r is the radius of the circle. And that'll give me one of these circles, right? That'll give me, say, this top one. Okay, because I have a top and a bottom, I'm going to need 2 of those, right? So I'm actually going to write that I need 2 pi r squared, okay, because I need both a top and a bottom. So then the next thing I need is the components to make the body of the cylindrical can, right? So this part. And like I said, if you unravel that cylindrical can, you end up with a rectangle that looks like this. Okay, so we really need what is the area of this rectangle. Okay, to find the area of this rectangle, I really just need to know the height of the rectangle and then the length of the rectangle, right? So, or the width of the rectangle. Okay, and if I know those two, then I can figure out its area. Right, so if we try to write down what the height and the width of this rectangle are, you can see the height is just going to be this same height over here, right? So this length right here is really that same h that we had before. And this red part, right, so the width of this, you can see this comes from unraveling this, and this length right here comes from this circle, right? So imagine we took this circle up here, we maybe cut it right here, and then started unraveling it, right, and then laying it down flat. Okay, so the length from here to here, right, so this whole length is really the same as the length that it takes to go around there, right? So this length right here is really just the circumference of this circle. Okay, so if we write down an equation for the circumference of that circle, okay, so the width of this box here should be the circumference of that circle, which should be 2 pi r, right? So that's the equation for the circumference of a circle. Okay, so if I now look at the area, so maybe we'll do that in purple here. So the area of this rectangle, okay, it should really be the height times the width, right? So when I write this down, I should write h times w. So instead of w, I'm going to write 2 pi r. Okay, so this equation is giving me my surface area, right? So surface area equals 2 pi r squared plus 2 pi r h. Okay, and this is what we want to minimize. We want to minimize this. Okay, because then we'll minimize the amount of surface area needed to make the can. So that means minimizing the amount of metal that we need. And that'll minimize the cost, right? Because we won't need so much metal. Okay. So that's step number 3, right? We've written down an equation that we want to optimize. Step number 4 is to write down a constraint. Okay, so somewhere in the problem, you're given some constraint. Okay, so here we don't want to spend too much money on the metal needed to make the can. But we can't just make a teeny tiny little can, right? Because we have a constraint. And the constraint is this first part of the problem, right? The constraint is that the cylindrical can needs to be able to hold exactly 2 liters of oil. Okay, so that gives us a constraint, right? That makes it so that we can't just make the smallest can possible, right? It still needs to be able to hold 2 liters of oil. Okay, so that's going to give us our constraint, right? We're going to write down our constraint. Okay, so we can write that down on the next page here. Okay, so our constraint, so this was step number 4. Our constraint is the volume, right? So the volume that this cylinder needs to be able to hold. So it needs to be able to hold 2 liters, and I'm actually going to turn that into centimeters cubed. So 2,000 centimeters cubed. Okay, and if you think about, okay, do I know a formula for the volume of a cylinder? And you actually might, right? And if you don't, then that's something that you would look up. So if you have a cylinder, okay, let me try again. A cylinder, okay, so that's as close to a cylinder as it's gonna get. Okay, so if we had a cylinder like this, and it had some radius r and some height h, right, its volume would really be given by, so it should be pi r squared h. Okay, so this gives us an equation, right? So I'm going to put this all together here. So this really gives me my constraint equation, which is pi r squared h equals 2,000 centimeters cubed. Okay, so that's giving me my constraint, right? This is an equation that describes the constraint. Okay, so that's step number 4. So if we look back at step number 5, so 5 and 6, maybe we'll read them together. So number 5 says you want to use the constraint equation to rewrite the equation that you want to optimize. Okay, and then step number 6 says, okay, you should have an equation now that you want to optimize, so optimize it, right? Find the critical points and figure out what the max and mins are for that function. Okay, so the idea is that you have this formula right here, this equation. This is a function with two variables, right? An r and an h. Okay, we want to find the minimums for this function, right? We want to minimize it. We have a way of doing that, right? That's finding critical points. So you take the derivative, set it equal to 0, and then figure out whether you have a maximum or a minimum. Okay, but we don't know how to do that with equations that have more than one variable in them, right? So here we have r's and h's. We don't know how to take derivatives of functions like that. Okay, but if we can use our constraint to try to substitute or eliminate one of these two variables, then we'll have an equation with just one variable in it, and then we can take derivatives, set it equal to 0, find the max and the mins. Okay, so the goal now in step 5 and 6 is to rewrite your constraint so that you can substitute into here, and then you can rewrite the equation you want to optimize, and then you go ahead and optimize it. Okay, so let's do that on the next page here. So we have step number 5. So actually before step number, so yeah, we'll do it here, right? So step number 5, I'm going to rewrite my constraint, right? So I'm going to rewrite this equation right here. Okay, so I'm going to solve for one of these two variables, r or h, right? Maybe I'll solve for h just because it looks easiest. So if I solve for h, I'm going to get h equals 2000 over pi r squared. Okay, so that's what I get when I solve for h. Now I want to use that so that I can substitute into my equation for s, my surface area, so that then I can have the surface area written in terms of just one variable, right? And in this case, that'll be r. Okay, so let's take that and substitute into the equation for s. Okay, so if you remember, s was the equation 2 pi r squared plus 2 pi r h. Okay, so instead of h, I'm going to write 2000 over pi r squared. Okay, so now we do a little bit of simplifying here. So these pi's are going to go away. This r is going to cancel with this. And then we're going to be left with, so we'll be left with 4,000 on the top. And in the bottom, we're left with an r, right? So 4,000 over r. Okay, so this is the equation for s that we want to work with. Okay, so that's essentially step 5, right? I've used the constraint that we had to substitute into s, and now I have this formula for s, right? So look, now it only has one variable in it, this variable r. Okay, and that r is going to be what we're trying to solve for, right? So r is the radius of the can. That's one of the dimensions that we need. Okay, so step 6 is really optimize it, right? So now find the minimums for this function s. Okay, so to do that, we take the derivative of s, right, and set it equal to 0 so that we can find our critical points, right? So take the derivative. Okay, so I'm going to get s prime. So remember, r is the only variable here, so the 2 pi is just a constant. So I'm going to write 2 pi. The derivative of r squared is 2r, okay, plus, so now if we think of this as, so this is the same as 4,000, so this is the same as 4,000 r to the minus 1, right? So if we think about that dividing by r as just a power, right, these are the same, okay? So then we can take the derivative of this, right? That's a little bit easier to see what the derivative should be. Okay, so the derivative should really be 4,000 times the derivative of r to the minus 1, which should be minus r to the minus 2, right? Because I pulled down the power, right? That gives me this minus, and then subtracted 1 from the power, right? So there I get that minus 2, okay? So now let's go ahead and rewrite this so it doesn't look so messy. So this is 4 pi r minus 4,000 over r squared, okay? And I'm actually going to go ahead and put these two terms together, right? So I've got a term here, I've got another term here. I'm going to get a common denominator, and I'm going to put those together, okay? So s prime is really, so I'm going to multiply this first term by r squared. So I get 4 pi r cubed minus 4,000 over r squared, okay? So now the next step in finding max and mins is setting the derivative equal to 0, right? Once you find the derivative, set it equal to 0. So set equal to 0, okay? So we're going to have s prime, this is 4 pi r cubed minus 4,000 over r squared. We're going to set this equal to 0, okay? So a fraction like this is equal to 0 only when the numerator is equal to 0. So you can think of it as multiply both sides by r squared. So this r squared gets canceled. Over here, if we multiply 0 by r squared, we still just get 0. So really we end up with 4 pi r cubed minus 4,000 equals 0. And now we can solve this for r. Right, so maybe draw an arrow this way. So solve this for r. You should get r equals, so you're going to add the 4,000 over to the other side. You're going to divide then by 4 pi, right? And then you're going to take a cube root. Okay, so I'm going to let you go through the particular steps, but you should end up with the cube root of 1,000 over pi, okay? So that's what you should end up with as a solution for this equation, okay, for this equation, okay? So this is actually giving me what the minimum is for my function s, right? So that's what we just found. So that means if I have this r, so this radius for the can, then that's going to produce the smallest surface area. Okay, we do still need the height of the can, right? So maybe we can write that down in the next page here. So r, we ended up with the cube root of 1,000 over pi. And if you punch this into a calculator, it's about 6.827. Okay? So we still need the height, right? So if you look back, the height we got to be, so we can look right here, right? So here it is, height in terms of r. So we can use this to figure out what the height should be. So the height should be 2,000 over pi r squared. Okay, so take the number we just got for r and plug it in. And we should get something around 13.6556. Okay? So what we've just found is the dimensions that give the smallest surface area for the can are, so are the ones that we have up here, right? So are precisely these. Okay? And so we can move that here, right? So are these. So that means if we're working for this company making these cans, if we tell them, well, make the can so that the radius is this number and the height is this number, then your can will use the smallest amount of metal possible, but it will still yield a can that can hold 2 liters of volume, right, of oil. Okay, so these together give us our solution, right? These give us our dimensions.